today we're going to talk about, by the way, this is sort of, in a certain sense, this is almost the last new section that we have before the test. We do have 4 to cover, but there's really nothing new in that. It's just all about practicing curve sketching, which we've already started to do. In fact, today on the quiz, you can expect just a little bit of what I'm going to talk about today, what we call rule and some curve sketching, and you can expect a quiz on Tuesday that looks almost the same, curve sketching and a little bit of culture. So that's kind of a heads up on that. And you may wonder why I freaked out and did 4-7 before we did 4-4. And the reason for that is local talk rules about limits, and knowing that rule will help us do curve sketching more accurately. How many of you have ever heard of local talk? Heard of it? How many have you ever used it before? You might have. What's it? Right. Did you have any exams in 1040 where it said final limits you're not allowed to use local talk rule? Right. Yeah, they didn't teach it, but they tell you not to use it if you already knew it. Right. Well, L'Hopital's rule is a really groovy rule that makes taking certain limits easier. Let me make a couple points. Number one, it doesn't always work, right? I mean, there are some situations where you just don't want to do it. And one of the most important things about learning any new math rule, you need to learn when to use it, you need to learn when not. All right. So let me give you kind of a couple of motivating examples. So here are some limits that I just kind of scribbled down. We'll look at. Okay, so here's some limits. By the way, what's the first thing that you should always do if I ask you to do one of the limits? What's kind of the first boneheaded approach that you make? Right. So, for example, let me ask you, what's this limit? As x goes to 0, of x squared plus 1 over 2x plus 4. What is this limit? This limit right here is 1. How did I get that? It's just freaking plug it in, right? That's the first thing that I always look at. What happens when you try this here? You got 0 on the top, but you got 0 on the bottom. Here, 0 on the top, 0 on the bottom. Here, 1, 2, -1, 0 on the top, 0 on the bottom, right? That is a message from God telling you that there's more to be done on 0. You've probably seen both of these limits before, because both of these limits are very important in proving that the derivative of sine is cosine and the derivative of cosine is sine. Anybody know what this limit is? That is correct. This one is 1, and this one is 0, 0. How did they show you how to do that? Did they draw like a triangle and do some stuff? But this is the rule. Okay. So you know this is rules. If you actually try to show this, you can do this doing all kinds of trigonometry. Yang, these both come from the squeeze theorem. It's complicated, right? Now we're going to see actually how to do this. This one we can do. What happens? You get 0 over 0, right? I'm going to do this one. I'm gonna go ahead because we have the technology to do this. When, as X goes to 1, and this is actually kind of a good review. Basically, some algebra problem polynomials. So if I'm a bonehead and plug in, I get 0 there, right? How can we move forward with this? Backward. Because here is in fact, when I plug 1 in here, I got 0, right? That means this has to have a factor of x minus 1. And so you can do polynomial division and you can just divide in easily or without a remainder. See, this should be x to the 4th. So that gives me x5. I need an x4, so I need another 2x cubes. I've got no x cubed over here. So that's going to be minus 2, so plus 2 squared. That. Let's see. I get a minus 3x squared. So there's minus 2 minus x. And let's make it minus. See. X to the 5th. 2 minus 1 is x to the 4th. 2x cubed minus 2x cubed 0. Minus x squared minus 2x squared minus 3x squared. Minus x plus x gone. Nice, right? But a pain in the butt, right? And you know, factorization is my bread and butter, so you gotta do the same thing below. Let's see here. This should be an x squared. And let's see, then I've got an x squared and I need a 3x squared, so minus 2x. And let's see, what do I need to add? Not minus 4, so plus 4. Yes, that's right. So this gives me x cubed minus 3x squared plus 4x. Oh, so that's somehow. Let's see, what did I do? 6 cubed minus 2x squared. Oh, there. It's going to be minus x squared plus 4x. Again, x cubed, 4x squared minus x squared, 3x squared, plus 4. And that's going 4x minus 4. So see, I'm going to mistake there. Now, what do you do now? Here. And now if I try to plug in again, x4 plus 2x cubed plus 2x squared minus x minus 1 and x squared plus 4x plus 4. I get plugging in 1, 3, 5 minus 2 is 3. And that's 9. So I get 1/3. But obnoxious, right? I think we can all agree this is an annoying problem. So let me record this over here. What do we get? 1/3. And you all, the folklore that you gave me was this, what, 1 and this was 0? You look forward with it. Show you how this is. So there. And there's technical considerations here, and we do. I suppose. F of X, G of X are differentiable. So we can take their derivatives. On an open interval. And G prime of X is not zero on I, except maybe in fact, it will often be zero in one of the cases. If limit X goes to A of F of X equals zero, and limit as X goes to A of G of X. Both of these happen, both of them zero. Or limit as X goes to A, F of X plus or minus infinity, and limit as X goes to A, G of X plus or minus infinity. Then the limit as X goes to A of F of X over G of X is the limit as X goes to A that the prime of X. Prime of X. By the way, slope total. Do not confuse this quotient. We're not taking the derivative. That's a given. This is something new. Derivative of that prime derivative. Provided limit as X goes to A limit on the right exists, or is plus or minus. If you get this limit does not exist, this limit could even be infinity or negative. If you get one just wiggling around and it doesn't exist, then L'Hopital's rule doesn't apply. You have to start over with something else. This also applies if X is plus or minus infinity, or limit is from left to right. So L'Hopital's rule applies to left-hand limit, right-hand limits separately, or yeah, and everybody. Now, let's do some problems, and then I want to talk a little bit about theorem. Let me show you utility of L'Hopital's rule. Okay, let's be a bonehead and plug in. X equals 0, cosine is 1, so I get 0 on the top, get 0 on the bottom. Great. Let's start L'Hopital's rule with this. What's the derivative of cosine? Sine. Derivative of X is 1. What's that limit? I got to plug in. How about this one? If I'm a bonehead and plug in, it's 0, it's 0. Let's do L'Hopital's rule. Derivative of sine x is what? Cosine x, derivative of x is 1. Plug in. I get it. Let's do this one right here. If I plug in, just like I did before, I get 0. Follow the golf rule, this should be 5 x4 plus 4 minus 6x over 3x squared plus 6x. Now, when I plug in here, I get, when I plug in 1, I get 9 minus 6 is 3 over 9. And then 1/3. Out in 5 seconds. That's certainly super much quicker. So local cultural is very utilitarian. Okay, so one of the things I'm going to do is let me illustrate what this little caveat is, right? So this is kind of an easy rule. If it's 0 over 0 or infinity over infinity, then actually I'll do it in infinity. And then I'll okay, so this example. By the way, you'll put your eyeballs on that and tell me what the end is before we do it. You actually have the technology to do this. Can you look at that and tell me what the end should be? I think it's 1/3. Somebody tell me how to think of it. Let me ask you this. What's the highest power that you see on the top of the thing? 2 powers, right? And its leading coefficient is, what's the highest power that's on the bottom? Also 2. Ding, 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 you got a match. Its coefficient is 3. So that should sort of cancel out. In the old days, you would have done this. And actually, I want to multiply top and bottom by 1 over x squared. And this is 3 minus 2 over x plus 4 over x squared. 1, 5, 3 minus 1 over x. Everybody okay? Now, as x goes to infinity, this animal and this one all go to 0, don't they? And that leaves you 1/3. However, L'Hopital's rule works as well. If I'm a bonehead and plug in, I certainly get infinity over infinity. All right. Right. Now, what happens? I get infinity over infinity again. Right? So it looks like I'm not done, right? Because I still got infinity over infinity. That's okay. L'Hopital's rule, just do it again. derivative of this is 2. And that limit exists. Get 1 point. So what cultural, pretty easy to implement in this fraction. And you know, oftentimes it's very quick. Now I'm going to give you a couple of situations where you got to avoid it a little bit, and then I'm going to do some more sophisticated application. This is only set up for fractions. Local cultural set up for fractions. Bill over bread, right? And this is how you work. What happens if you have a product of 2 things, etc.? And I'm going to show you how to get around that. Let me first say something about this caveat. Provided the limit on the right exists, or is it plus or minus? Let me do this. Let's look at the limit. Thanks to infinity. It's by the way, anybody wants to stand what well, let's do it. As X goes to infinity, push the bottom bit. That's getting very, 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 very hard. Function. What about the top? I claim that the top of this fraction is also going infinity. So explain. I mean, I get it. This piece is getting very, very large. What about this piece right here? What happens to 2 sine x? It doesn't go anywhere in the certain sense. It wiggles back and forth. If I agree with that, it goes between +2 and -2, +2 and -2. I agree. But the top is still going to infinity, right? Because this is going back and forth between +2 and -2. But this is getting huge, right? So the top's going to infinity. So let's try what the top. It appears to apply. What's the derivative of the bottom? What's the derivative of the top? What is local cultural receiving telling you? What's the limit as x goes to infinity? 2 cosine x plus 1. It doesn't exist at all, right? 2 cosine x lays back and forth between -2 and 2. Great. 2 cosine x plus 1 just kicks it up. So now it's waving back and forth between like -1 and 3. Great. So this limit does not exist. So L'Hopital. Does not apply. In fact, if you're not careful, you might say, oh, look, this limit doesn't exist, but actually it does. That's why we say this limit exists. This limit does not exist, so I shouldn't have done L'Hopital in the first place. I got to start over. By the way, what is the answer here? That limit is 1. Let's do this again. Instead of doing all that L'Hopital stuff, what really applies here, multiply top and bottom and form of x. So this is 2 sine x over x plus 1. And in the bottom, I have 1 plus 1 over x. Am I okay with that? Now, as x goes to infinity, where does this piece go? The radius goes to 0. What about this piece? This also goes to 0. So you better remember why that piece goes to 0. How many of you bring this, please? Then this is essentially it. Look at the numerator. I don't know why. I don't know much, but I do know the numerator is squeezed in. I agree. Always less than minus, always better than minus 2 less than 2. Divide this by x. And x is always positive since we're going to infinity. So this thing is between little guy and big guy. But as x goes to 0, where do these both go? 0. And so this goes to 0 minus x. And so what am I left with? 0 plus 1 and 1 plus 0. So I get 1. So there's a little situation where you want to be careful about what we call it. And occasionally, this is what might work. This is actually my favorite example. By the way, let me make a little note of here, because this will be useful problem. Okay, good chain rule practice. What's the derivative of x squared plus 1? So this is actually x over the square root of x. So, because the 2 and the half cancel. Everybody cool? Now, it's this way. If I'm a bonehead and plug in, everybody agree with my time. So let's try this out. Derivative of x is 1. And derivative of the other piece is right over there. I will simplify this. Because I need to stack it, right? Can I get that? Infinity over infinity, right? So, derivative of x is 1. The derivative of this is x. Somebody tell me why I should quit. That's right. This is circling the ball right here, right? Because I've gotten back in 2 steps where I started. By the way, anybody want to guess this is? Actually, this does show something. I don't know at this point if the limit exists, but if it exists, it has to be 1 of 2 numbers. Actually, this is. Yeah, if it exists, it has to be. Yeah, it doesn't 1 of 2 numbers. Actually, I say you're right. I guess that is certainly a possibility. How about finite numbers? 1 or negative? Because if this limit exists, it's equal to its own reciprocal, right? And so, yeah. So I guess that. But by the way, how would I do this? So this is kind of a failed local call tool. I need to be able to figure this out some way. Very good, very good. So I'm going to multiply top and bottom by 1 over x. But here I'm going to realize this is 1 of the square root of x squared. And you have to be careful with this. 1 over x, these two are the same because x is positive, right? If x, and that's okay because x is going to infinity. If x was negative, right, if we were going to negative infinity, I have to replace that by -1 where it goes. But here I'm okay, and so this is limit as x goes to infinity. That's a 1, and this is square root of 1 plus 1 over x. So I get. Yes. Why did you choose 1 over x? Because that's the biggest power that I see on the top and the bottom. Everybody agree? Do you agree that x is the first power here? And this does look like an x squared, but then I take the square root of it. So it's sort of like x is the first power. Why does this miraculous local call tool work? I'm going to give you a quick sort of sketch as to why this works in a special case. You want to see what there are. If you wanted to prove this in all its glorious generality, it requires what they stuff. In the special case where f prime of a and q prime of a 0, I think. F prime and q prime are continuous. F of a, g of a 0. So this is the old what we call 0 case. And Right. So I don't have to do what. So let me go through this. Okay, so let me take a step. Limit as X goes to A. This is the same as this, because I'm assuming both F of A and G of A are C. Right. So really, that's just a fancy way to write zeros. This may, why is this some kind of reasonable assumption? Because if I were to take this limit here, what's the first bonehead thing you could do? You would plug in A for X. And this is just the case where you get 0 over 0. Right? So this is not a reasonable thing. This is the limit. As X goes to A. Of F of X minus F of A over X minus A, G of X minus G of A over X minus A. What did I do to go from here to here? I just put the X minus A in the bottom. It's fractions, and I can cancel that out. We can say that. That quotient in the top, does that ring a bell? What does that look like? That's right. As X goes to A, this should be F prime. If I agree with you. Because that thing in the top, that's just the definition of F prime of A. This is the definition. Y'all remember the correct. And because we're assuming that F prime G prime is A, this is the limit as X goes to A of F prime X. So that's L'Hopital's rule in that special case. Okay, here's one. Let's look at the limit. Okay. If I plug in, by the way, this is one that you calculate the pooling on. If you put in, like say 0.00, put like 6 zeros, unless you have a really big packet, just put in 0.03341. You do this, it'll tell you that it's 0, but it's actually not. Okay, so if I'm bonehead to plug in, I get 0 at the bottom. Root of X is 1. And the root of this thing we've already done is X square root. Now when I put in 0 correct, What happens if you do this, let's change this a little bit. What happens now? Right? Now just keep at the bottom. Right? So in other words, this one is now going 0 a little bit faster. Again, I get 0 to 0. Find the control field. This is going to be 2x. And this is going to be x square root of x squared plus 1. Now, let me give you kind of a little help with this. I'm going to do a couple other problems here. You do what we call rule again, right? Because you get 0 on the bottom, 0 on the top. Right? No. Anybody see some stuff? In particular, you see something you cancel an X from the top and bottom. So let's rewrite it this way. This is 1 over 2. That limit I can evaluate doing nothing up more than plugging in. This is 1.5. Now again, I could have done what I'll do again by taking the derivative of this, which nobody wants to do, and the derivative of this, which is not so bad. It's like a big mess. When you do multicultural, if you see the easy algebraic simplification to do, you see stuff that cancels and cancel out, right? If you have a product of two things, so suppose you have a fraction. You have Bill times Fred on the top. You have Bill times Sarah on the bottom. You want to cancel Bill, because otherwise, when you take the derivative of that, it's going to be a big product on both the top and the bottom. Right? So canceling things. Example. Over. What's this one? I don't know about you guys, but I've always been dying to know what this particular limit is. And today is my lucky day. Right. Now, what happens if you plug in the top? Right? This gives you a 1. That's a 0. That's a 1. That's a 1. So everything's a 0. Right? 0 on the top. What happens if you plug in bottom? It's 0, and then you get a 1. So it comes to 0. So you get 0 to 0. You can do what we talk with. Who wants to take the derivative of the top and the bottom? Nobody in the right mind wants to do this, right? Anybody think the way when I plug this in, I got 1, right? Just to this piece up here. That piece gave you 1, that piece. The only reason this thing is 0 on the top is because of this. This was the bad one, the offender. All right. Look at the bottom. Secant of 0 is 1. This is the only reason the bottom is. So let's try this. Actually, I don't need to talk through on that one, but anyway. We'll limit this times the rest of the stuff is the product of limits. If both limits exist. So we've got to make sure. What about this? Here's the side. Actually, that's just close. But I'm gonna do. Everybody agree 0, 0 here. So this is limit as x goes to 0, cosine x over secant squared x. Great. And this piece is 1. So this limit here is 1. And all you gotta do here is put in 1, 1, 1, 1, this 1. So this whole limit. Everybody agree with it? Yes. Do you advise us that? Personally, I don't. I know. Like secant squared. Do you know? Do you know what happens when you put in 0 to cosine? Right. And so secant is reciprocal of cosine. So secant of 0 is also, and then square. Still. Right up here. The moral of the story is I took out all the appendix, ones that are causing the 0 over 0, they did separate. These ones, they don't contribute to the badness of the limit because you're getting numbers out of it, right, that are not being. Right? So the point is, you could do what we told them straight up derivative of this, right? And you can get the right answer, but that's it. Okay. Here's another one. This is one of my favorites. Sometimes you have to have patience with what we call. After this. Oh. Anybody want to guess what this one is? I was at 1/6, right? I mean, it's kind of crazy that it doesn't seem like it'd be 1/6, but let's try it. If you're a bonehead and plug in, what do you get? 0, 0. If I agree with that. So let's just go ahead. X squared. What's the derivative of time? Cosine x minus 1. So there's my first iteration of the algorithm. So I try to plug in again. 0 on the bottom, 0 on the top. Well, it still smells like we need local algorithm, so let's try it. Derivative of cosine and negative sine. Derivative of this. 6x. Still, I have 0 over 0. Right. How about that? Now, when I get In this particular case, I had to do a total rule 3 times. Give me any positive number. 8675309. I can set up a problem where you will have to do local call rule that many times. Right? Don't worry, I won't do it because then I have to grade. But point is sometimes you have to be patient. Okay. Okay, here's one. Speaking of patience with local call rule, here's a big engineering. And actually, science as well, because if you've heard in computer science about whether you can solve the problem polynomial time or exponential time, or heard of these kind of things, there are some problems that, in fact, who has heard of public key cryptography? Part of it. This is the way that, like, for example, banks hide your money from online hackers. It basically hinges on the fact that if you factor, if I give you a 60-digit prime and a 60-digit prime, you multiply those two together, you get 120-digit number, right? Now, I multiply that together and I give it to you and I say factor. It takes you a long time. Like, I mean, it could potentially take, if I make the prime the two pieces long enough, it could take longer to get you factor that. That is essentially how one of the ways that communications are disguised of the internet, right? And the reason that this works is all the algorithms known so far, when computers factoring large integers down into their prime components, there's no algorithm that goes polynomial times. All of them are exponential. One of the important things in computer science and in engineering is powers of X small compared to how fast the exponential. How many of you have heard of this? Exponential growth, right? Ooh, that's big. Exponential. Polynomial growth be fast, slow. Here's why this is true. So again, one. Integers. Take the limit as x goes to infinity of x to the n over p to the x. And look at how we quickly reveal to us why exponentials are much bigger than polynomials. Now, maybe this is x to the 100th power, which certainly grows very fast. Right, x to the 100th power. I think probably if you look at that function, like it grows extremely fast. E to the x. In fact, this grows faster than this at first. Looks like, for example, if you have 2 to the 100th power, that's very, very large, right? I think you're probably approaching the number some type of part of the universe. Very large. This e squared is less than that. Right? So it looks like this one, it's almost like a cheated race. It started off very quick. At 1, these are at 1, this one's smaller than this. At 2, this is much bigger than this. At 3, this is much bigger than this. At 4, this is much bigger. The exponential catches up. Let's see what the Vulcan has to say about all this. Infinity over infinity. Great. So what the Vulcan rule says, you need to try. Derivative of x, the n power is, and the derivative of b to the x doesn't budge. Now you go over power. Okay, still got ostensibly you've got infinity over infinity here. Ostensibly, you still got in factorial over here. Obviously, you still got a video here. Keep going. By the way, can anybody tell me what you're gonna get? So actually, let me do that more. N minus one, n minus two, x n minus three, dx still. You see, I don't want to see what happens when you get to x to zero. What do you do? You get your n minus one, then still there, n minus two. And where does it stop? Right, it looks like it stops one higher than the exponent. Everybody agree with that? So it should stop at one. Everybody agree with it? But the bottom is still eating the x. What's a shorter name for this thing on top here? This is n factorial. And when you reach the state right here, because big that may be, but it's still just a number. The exponential goes to infinity. So no matter how big power of x, the exponential eventually kicks its butt. Right? And that's why we say exponential growth always overpowers polynomial. Any questions? Well, so we've dealt with fractions, 0 to 0, infinity, right? There are other things that you might concern yourself with. And that is, for example, this. What do you think? You bet what the problem is with finding this answer. Right. What happens to the log of x as x goes to 0 from the positive side? Let me scribble a little log x over here. Find it. As x goes to 0 from the positive side, this is going to make infinity. But this is going to 0. So the question is, who wins? What happens when you have 0 times infinity? Always. It depends. It's like a race. If you're going to 0 much faster than you're going to infinity, if you're going to infinity much faster than 0, you get infinity. If they're pretty close, you might get 27. Let me illustrate this really stupid example. But often stupid examples illustrate. No. What's this? This is a bit. Now let me write this. Right, agree. That should be the same. Where's this piece going? This piece is going to zero. Right? And this piece is going to infinity. Infinity wins the race. Everybody agree? One for zero. Everybody agree with that? This is going to zero. This is going to infinity. And this time zero wins place. Okay, and the next one. I'll give you that. Give me a positive. 14. It's very smart LED. X is canceled. This is 14. All right. This one is going to infinity. And this one is going to zero. But the growth rates are very, and it turns out to be 14. So when you get infinity times zero, anything can happen. So let's go back. This. Zero, negative infinity. I would really like to use L'Hopital rule, but this sucks because L'Hopital rule set up fractions, and this is not a fraction. Don't say fraction. All right? Make one. All right? Force the issue. Now what do we have? Top is going to negative infinity, bottom is going to plus infinity. L'Hopital rule. What's the derivative of log x? And this is x to the minus 1. Derivative of that is minus 1 over x squared. Now, please, as I advised before, don't do L'Hopital again. Simplify this answer first. And actually, zero wins this. How about this? Okay. Common bone head and plug in. I get a zero here. I get a sign. See that thing inside there is 1 0, right? 3 over x sign 0 0. So I get oh, I'm sorry. Here. This is actually going. This okay. By the way, What is this? I didn't write that. What is this? This one is- What's happening with this piece? I think we can all agree that this is great. What happens to the sine of 3 over x squared? It's actually equals to 0. It's freaking out, right? Because the angle, the 3 over x squared is growing very fast, right? And then you're taking the sine of this, so it's wiggling back and forth between plus and minus 1. Everybody agree with that? But this is going to 0, and this is never getting bigger than 1, so this actually is. This is a squeeze. This is what I meant to write. How about that? Now, the first chunk, the x squared, is going to infinity. And the other piece, the 3 over x squared, is going to 0. So x squared is going to infinity. Sine of 3 over x squared, that's going to sine of 0, which is 0. So I've got another one of my patented infinity times 0. What happens? Let's do what we did before. This isn't a fraction. Make it. Now I have sine 0 over 0. So cultural work for me, hopefully. This is minus 2 over x cubed. Remember, this is x minus 2 power minus 2 x to the minus 3. And this is sine of cosine of 3 over x squared. But derivative what's inside here is minus 6 over x. Again, stuff out. The x cubes will cancel, and the minus 6 minus 2 will cancel out to 3. Infinity of 3 cosine 3 over x squared. As x goes to infinity, 0 3 cosine 0. So here's an infinity times 0 that ended up being 3. This one right here. That's 1 over. So what I did is I put these square roots down the bottom, and that. Other questions? Um, actually, sorry. This is another color, right? This doesn't look like a single fraction. Look at what happens here when x gets very, very close to zero. The one over x piece is going to infinity. Everybody agree with that? Since x is getting very close to zero. The positive side is huge positive side. One over sine x also going to infinity. So this is sort of infinity minus. Any ideas on how we might follow the problem? I want a single fraction, right? What do I have? Two fractions? Find the freaking common denominator. There we go. Algebra is now your friend. Notice the first piece is sine x over x sine x. Second piece is minus x over x sine x. Right. If I plug in, I get 0 minus, so I get 0 over 0, try to solve rule. At the bottom is sine x plus x cosine. That's the derivative of. Now, if I plug in again, I get 1 minus 1, 0. Then we get 0, so you get 2. Let's try to plug in one more time. Derivative of the bottom is cosine x plus cosine x minus x sine x. That's piece of product over here. And root of the top is minus sine x. And finally, at this point, I can plug in. When x equals 0, I get 0 over 1 plus 1 times 0, 0 over 2 times 0. Question. Okay. The hardest of Paul's applications are the ones where you have variable base and variable exponent. So one infinity, 0, 0, infinity. Then you find e bar next. Okay, so let me see things. Let's do. Sex modes. Okay. Here we have a variable base and variable exponent, right? Look at the base. What is happening to the base as x goes to 0? Forget the 1 over x exponent. What happens to 1 plus sine of 2x? It's getting close to 1. Just plug it in and get right. What's happening to the exponent? The exponent's going to be very large, right? It's going to infinity if x is positive and negative infinity if x is negative, right? So what you have is this number that's trying to go close to 1, right? Very high power is 1. Doesn't matter how, if you actually have 1, it doesn't matter what power it is, it's still 1, right? But here's the problem. This is cruising in toward 1, and this is getting very large. So again, you've got a race going, right? You're tempted to say 1 to the infinity power, which should be 1. But again, the race is on. If this goes to 1 faster than this is going to infinity, it might be 1. But if this sort of goes to 1 very slowly, and this is getting big very fast, you could go to infinity, and there could be anything in the middle. Let's see what happens. But my goodness, how in the world am I going to get a L'Hopital's rule out of this? You can take a log. There's a place to do it. This is the way I like to do it. Because this thing is the same as the previous, right? These log, right? Everybody okay with that? And this allows bring down the x. Gotta love it. Everybody okay with that? Now, what I want to do here let's do a little bit. By the way, so I say I'm going to take a little side here. I want to find the limit as x goes to 0 of 1 over x and plot on this side. Can anybody tell? Anybody smell what the rock's cooking here? Where am I going with this? Right. The idea is this is the exponent in the original problem, right? So what I'm trying to do is I'm finding out where does this stand. And once I find out where it goes, I can just plug it back in here, right? Remember, the exponential is a continuous function. So to find the limit of e to the blob, all you have to do is find where blobs go and plug it back in. So let's do the side problem. L'Hopital's rule, I need fraction. But fortunately, one is pretty much divided from here. Do I agree with that? So the 1 over x conveniently allows the right form. Now as x goes to 0, where's my bottom going? 0. Where's my top going? log of one, which is zero, right? So this is prime for local polynomial. Derivative of x is one, and derivative of this top thing is one over one plus sine of two x times what? Okay, times cosine of two x, gotta have the cosine plus the sine, times two. Which is so this is the limit as x goes to zero of two cosine two x over one plus sine two x. And when I plug in x equals zero, I get one times one plus zero on the bottom. So the exponent here is going to. So what's my answer? Where's this thing going? Right. Question. Yes. Or right, and that's the whole thing. So if you're just given right in front of you a fraction, if it's 0 over 0, infinity over infinity, plus or minus infinity, then you can just go for it. Some of these other ones get to massage them a little bit, right? And this is the biggest massage of all, because when we deal with variable basis, variable exponent, you're almost always going to use log to combat that same problem with that exponent down, and then do an ordinary L'Hopital's rule over the exponent. Let's do find the limit. X goes to infinity. One plus c x squared actually, yeah. Okay, again, in my preliminary analysis, this x is going to infinity. So you're 1 over x squared. Right. So 10 0 0 6 1 basically 1 is going to infinity. So it's 1 to the infinity. It's no 1. So let's do the same strategy. 4 Okay, everybody okay with that first step? So this is then x goes to infinity. E 3x squared natural log 1 plus n 1 over x. So really, what I need to do is I have this here. And actually, in this one, I'm going to do a little trick. Just to kind of expand the horizon a little bit. Let's take a look at the side. Find limb as x goes to infinity. 3 log 1 plus n 1 over x squared over 1 over x squared. And just to kind of gut check me out on this one, get back to root 1, multiply top and bottom by x squared, multiply x squared at the bottom, that's 1, that's going to put that x squared. Everybody, okay, that's cool. Now, if I just plug this in, I get x squared infinity, 0 at the bottom, I get 3 times log of 1, so I can 0. Everybody okay with that? Now, this is pretty easy. You can just go from here to the. I'm going to show you another way to do it. Also with local aspects. Well, what's obnoxious when you take the derivative of this? The negative power of x. Everybody agree with that? Here you're going to, there's going to be some kind of secant squared, and there's going to be a negative power of it. Let me make it a little bit easier. So let's do this change of variable. Let's let theta equal 1 over x. So this now becomes limb 3 natural log 1 plus tangent theta. Ooh, easier to take the derivative of over theta. Everybody agree with that? Plus the 1 over x squared with theta. Here's the surprise I have to say. X is going to infinity. There's no x's. So its theta is going somewhere. Where is theta going? Very good. Right. X is cruising to infinity. Theta, x is getting very large. Theta is getting very close to 0. Right? In fact, you're right in spirit. It's actually 0. It's not quite 0. What is it? It's 0 from the positive side. Right? Because x squared is always positive. Right? So there's no way that theta is 0. So you're only coming in from one side. That doesn't matter. For this problem, it doesn't matter a whole lot. Distinction. Right, okay. Now let's do L'Hopital's rule, because again, we have 0 and 0. This is the limit. Theta goes to 0 from the positive side. Derivative of theta is 1. Come up here with this theta. Derivative of this is 3 times 1 over 1 plus tangent theta times secant squared. And when theta goes to 0 from the positive side, this is 3 times 1, 0 times 1, 1. So the answer to our problem. Yes. What's it? Because now thetas are variable, derivative of x is one, and x are variable. Now thetas are new variable at derivative of x. Yes. Oh, it's not one of those things, it's squared. Right. Okay, other questions? All right. Okay, let's try this. Okay, we'll do this for you. What happens about this? Well, recall. The limit, if x goes to zero from the positive side, of x log x, 0. This is a problem that we actually get over today. Right? So this is in the form 0 to 0. That's another one of these. 0 is 1, something else. Let's find that. Same strategy with variable base, variable exponent, or limit as x goes to 0 on the positive side, e log x, x log x, which is when as x goes to 0 on the positive side, e x log x log x. Like that. Okay. So now it is appropriate time for a little aside. We try to figure out what happens to that x. So my big question for right now is let's evaluate the limit as x goes 0 from the positive side of x natural log x 1. Here we have a 0 times infinity. And so what we told you is that I need a fraction root 1 over x is minus 1 over x squared. And this log it 2. What a mess. This is limit. X goes to 0 from the positive side. Let's multiply top and bottom by minus x squared. So let's bring minus 2x. Minus x squared. Power that. X. And this is 0. Because we already have that. So that limit is 2 times 0 is 0. This time it turns out to be okay. Any questions on that? Okay. We can take our quiz now, and